All right, we're going to start a new chapter, chapter 3, which is all about exponential functions and their graphs. So we're working our way through different types of functions and looking at the behavior of their graphs and what applications that they would have in real world settings. So chapter 3 is all about exponentials and then eventually their inverses. And hopefully you can remember what the inverse of an exponential is. We'll talk about that later in the chapter. So our essential question for today is how can I recognize and evaluate exponential functions with whatever base A is just a number, and then graph exponential functions and use the one-to-one property, which has to do with is the inverse going to be a function? So we'll talk more about the inverses as we go through the chapter. So recognizing, evaluating, and graphing exponential functions is what we want to be able to accomplish for this first part of 3.1. Exponential functions, what are they? Well, an exponential function with base A is defined to be f of x equals a base, whatever that is. So A is just a number raised to a power. So notice where your variable x, the independent variable, is your input. It's in the exponent, so hence the name exponential. That's why they call them that. So the thing that's changing that our value of the function depends on is the power, the exponent. So a couple things to note about the A: it has to be greater than 0, so the bases are always positive. It can't be 1 because a base of 1 is pretty boring. 1 to any power is just 1. And the x, though, the power is any real number. That means the domain of an exponential function is all real numbers. You can use whatever you want. So to evaluate something that has an exponent, I know we know how to deal with this, but 5 raised to the 3/5 power, let's just do a little housekeeping on our calculator, make sure we're okay with how we would type something like that in. So we would do 5 and then raised to the, and then you can type in your 3/5 however you want. You can use the fraction function, 3/5, whatever you want. Obviously, exponential functions get a bit messy. They get really large, or they can be really tiny, and they're often not going to be whole number answers. So we have to talk about how we'd want to express those. Lots of different ways that people decide to do, and I'm going to do approximately equal to. I'm going to say 6 to 6. If I'm going to round to the 4th place or the 10,000ths, 5, then it would be a 2 after, so it would stay a 5. The decision on rounding and how we're going to express answers will depend on the application that we're doing. So just make sure you know how to type in exponents on your calculator. To get into this, I want to start with an example just so you can remember again what these look like. So I'm going to have you go ahead and graph on your graphing calculator, first of all, 2 to the x. So let's go into the y equals menu, and we're going to do 2 raised to the x power. I'm just going to do a zoom 6, a regular standard window here, and I want you to take a look at this graph. And I want you to answer the following things: domain, range, y-intercept, and do you see any asymptotes? So I want you to think about that original graph and answer those questions. I'm going to have you pause the video and do that for this graph. And then I'm going to have you do the same thing with the other equation, which is y equals negative x. I'm curious if you remember, or 2 to the, not y equals, 2 to the negative x power. So what does putting a negative with the x do to a graph? Think back to your transformations. If the negative is with the x, what reflection is that? Think about that, and then let's take a peek at the graph. Is that what you expected? Hopefully, yes. Please go through, and I want you to answer these 4 questions about these 2 graphs. All right, so for both of these, the blue and the red, so this is the blue graph here, just to be clear, and this is the red one. Both of them have a domain of all real numbers, so negative infinity to infinity. You can use anything as a power. 2 to any number will be something that you can calculate. Range, though, is a little bit different. Notice there are no values on this graph down here in quadrant 3 or in quadrant 4. And also, would it ever actually equal 0 or the x-axis? Is it possible to say 2 to some number is going to be 0? Is that even possible? Or negative x, doesn't matter. And if you think about it, they can get really tiny. You can have like really 2 to like negative 1,000. It'll get closer and closer and closer, but that end behavior, it approaches 0. That can't ever be equal to 0. So the range is above 0 only, so 0 to infinity, or some people might want to use the y value. So y is greater than 0, whichever way is easier for you to think about. Okay, how about a y-intercept? What does this graph have in common, the blue one with the red one? Well, they both share their y-intercept. And look where it's crossing. looks like it's crossing at 1. Think about that. If you put in a 0 for your exponent, what is any base raised to the 0 power? It's 1. So every one of these has a y-intercept at the point 0, 1. That's a key feature of an exponential graph. How about asymptotes, end behavior? Looks like we have horizontal asymptotes. Depending on which graph we're looking at, it could be the positive x-axis over here for the y to the negative x, or the negative x-axis if we're looking at 2 to the x. So the horizontal asymptote is the x-axis, depending on which way we're going here, if it's increasing or decreasing. So some of the other things we use to talk about graphs, if we look at the blue graph, it's increasing for all values of x. So the blue graph is increasing. The red graph, the negative x, is decreasing for all values of x. So this one is decreasing as x approaches infinity. So if we think about our end behavior and what happens on the graph, these are either all increasing or decreasing. I want to talk about one other way to write this second equation, and I think this is going to be an important idea for you to think about as we express these. Instead of saying 2 to the negative x, I'm going to think of it like this first. 2 to the negative 1 times x. Okay, and the reason I'm going to do that, because negative 1 times x is negative x, or opposite of x. What's 2 to the negative first power? 2 to the negative first. Remember, negative exponent means 1 over reciprocal, so that would be the same as 1/2 to the x. Important to think of it that way, because if you think of it as 1/2 to the x, that kind of makes sense to think about this decreasing. And every time you're taking half of the number, so every x that you put in there, you're going to take 1/2 of that. So it should be decreasing. Each amount is half of what it was previously. So bases that are larger than 1 versus less than 1 are going to do different things, right? When we think about what's happening, what are we multiplying by? So 2 to the x is doubling, 1/2 to the x is halving, right? Or getting half as big. So these are some key features about exponential graphs. They're either always increasing or decreasing. They have horizontal asymptotes. Their y-intercepts are the same. And the domain is all real numbers. The range bigger than 0. Now let's talk about some of the things then that we noticed about those graphs, just to kind of pull this together. For the a value greater than 1, so that's our blue graph that we did, like the 2 to the x, is it increasing or decreasing over its domain? Pause and see if you can fill it in based off our picture. So that one was definitely increasing, right? That was like the 2 to the x example. So like y equals 2 to the x is a great example for that. For a is greater than 1, so the base greater than 1, what would this, oops, I'm going to do this in the other color. So I want to circle that one. I'm going to do this in the red color so it matches up. So a to the x is increasing. What does a to the negative x do? Well, that one was the decreasing one, right? That was like the 1/2 to the x, because remember that's another way of saying that. So y to equals 2 to the negative x is the same as 1/2 to the x, decreasing over its domain. So it's always decreasing. So increasing when the base is bigger than 1, decreasing when it's less than 1 but bigger than 0, because remember your base is always bigger than 0. So for the graphs, the domain doesn't matter which graph you're talking about. The domain is always all real numbers. Anything could be your exponent. The range, always greater than 0. So I'm going to say parentheses 0, comma, infinity. So only numbers bigger than 0, because how can you say 2, raise it to a power and get a negative answer? Impossible, right? Because it's always going to be either something maybe really big or really small, but it can never be negative because the base isn't negative. So it's always going to give you that positive result. And the y-intercept, always the point, 0, 1, every single one of those, because anything to the 0 power is 1. And both of them have the x-axis as a horizontal asymptote. So really important key features of exponential graphs. All right, so let's talk about what happens as the base changes. So what I'd like you to do is go ahead in your graphing calculator and type in these 3. I want you to compare the graphs. Before you actually look at the graphs, look at the equations and see if you can predict what you think is going to happen. And then I want you to think about domain, range, y-intercept, asymptote. Are these affected as you change the base? All right, so here are my 3 equations. The 3 to the x is the blue, the 4 to the x is the red, and the 5 to the x is the black. Okay, so what happens? Let's talk about domain. Still all reals, right? We have numbers all the way across. Range, still greater than 0, so that's still the same. Y-intercept, look, they share that. They all have a y-intercept of 0, 1, because 3 to the 0, 4 to the 0, 5 to 0, still 1, right? Anything to 0 power. Asymptote, still the negative x-axis. What's the only difference between the graphs? Well, the black one is the steepest, right? So it has the steepest slope. Well, of course, you're multiplying by 5 instead of by 3. So at the same value of x, 5 to that power is definitely going to be a bigger answer than 3 to that power would be. So the larger the base, the steeper the graph. So the larger the base, the steeper the graph. But all of these things, domain, still all reals, right? Range, still only positives. Y-intercept, still 1. Asymptote is still the x-axis. So as you change the base, what it affects is the steepness or the rate of increase or decrease of your curve. All right, let's practice just to make sure we understand again that negative exponent, what that actually means. Just to be clear, I just want to make sure that you're okay with this concept. And then we'll get into actually looking at transformations. So how else could you write 3 to the negative x? Remember, that's the same as 3 to the negative first to the x, right? Because 3 to the negative first, negative 1 times x power to a power there. But 3 to the negative first is 1/3 to the x power. So whichever way is easier for you to think about it. Let's get some numbers in here. We know the domain is all reals. We can use, oops, -0. -1. We can use anything we want. So let's do something that's negative, something that's 0, so we can get the y-intercept, and something that's positive. Can you fill in that table for me real quick? All right, so we'll have 1/3 to the negative first. We'll have 1/3 to the 0, and then 1/3 to the first. Well, 1/3 to the first is just a third. Anything to the 0 power, always 1. What does 1/3 to the negative first mean? It means reciprocal. So that would be 3. So we can think about what that number would look like. So we're going to go ahead and graph those points. So let's see. -1, 3. 0, 1, and 1, 1/3. So we can get those points. Remember, we could have picked anything for our domain value. So I'm going to go ahead and, ooh, geez, can't see what I'm doing. Connect that with a smooth continuous curve. And we have a really great example of an exponential. Always decreasing in this case because the base is a third, right? So it's getting smaller and smaller and smaller, a third of what it was before. Y-intercept at 1, and we have a great example of what this graph looks like. And remember, it would be the reflection of 3 to the x, which would be going in the other direction, right? Increasing for all values. Something to think about when you look at your original graph here now. This is definitely a function. The blue graph that I'm looking at that I just sketched is definitely a function. It would pass the vertical line test that we're very familiar with, which means this green graph itself is a function. Something else to remember what we did earlier though this year, remember the horizontal line test? So I want you to remember about that. The horizontal line test, what does that tell you about? The horizontal line test. It tells you about the inverse, okay? So what I'd like you to do is think about horizontal lines going across this green graph or any exponential graphs. They would only touch 1 point, which means it's 1-to-1, only touches 1 point. What did that tell you? What do you know now if the horizontal line only touches 1 point? What it means is the inverse is a function. So I know when I get to talking about inverses or opposite operations for any exponential, that its inverse will also be a function. So it's a good thing to keep in mind when we look at a new relationship that we know what its inverse is going to be as well. So all of these would pass that same test. All right, let's talk about transformations. All right, so the really cool thing about understanding how transformations work, it doesn't matter what your parent graph is. The transformations, where you put the values in the equation, have the same effect on every single graph. So here's what I'd like you to do. I want you to think back to what your 4 to the x graph looks like. And you can have it on your calculator if you'd like, just that 4 to the x. I want you to predict by looking at each of these 3. So we're going to try this, and then we're going to take a little bit further. What do you think the effect will be on the graph? So think about what each of these number placements would do, say for a parabola or a cubic, and guess what? It's going to have the same effect on an exponential. So pause the video, think about what each of them do, make your prediction, and then graph them and see if you were right. All right, let's talk about the first one. Notice where that -2 is located. It's up in the exponent with the x, right? So it's with the x. That means it's going to be a horizontal transformation. It's going to be moving either left or right. And remember, if we think about how far this shifts from 0, think about how far is x -2 from 0. That's a +2 shift. Always think about setting it equal to 0 so you can tell what that shift is. So it's a +2, -2 to the right. So this is going to shift to the right 2. And again, you can type that in on your graphing calculator and see that. be super careful when you type them in that you actually do put the -2 in the exponent when you do that. So let's take a look at similarities and differences. What changes if you shift the graph to the right? Domain, still all reals. Range, still greater than 0. How about asymptote? Yeah, it's still the negative x-axis, but what switched? My y-intercept. It's no longer at 0, 1, because all the points shifted over. That 1 is going to be happening at 2 now. So 2, 1 is a point on the graph, and you can even check in your table and see that. So 2, 1, look at the red there. Notice how small those numbers get too really, really quick. So the y-intercept is going to change. It's going to be crossing the y-axis a lot lower because I shifted the whole graph over. But notice the horizontal asymptote does not change if you slide left or right. Okay, take a look at the next one. What was your prediction? What does the +3 do? Notice it's after the value of the function. So do whatever 4 to the x is and then add 3 to it. That's going to be a vertical change. That's changing something in the y value or the output. So this one is going to be up 3. And again, hopefully you took a look at that so you could talk about what happened. And again, make sure you get out of the exponent for this one to be aware of what's happening. All right, take a look at your two graphs. Again, we need to talk about similarities, differences. Domain, all rails, no breaks, every possible value. Range, now it's not just greater than 0. We actually, the whole graph moved up. So now the range is actually greater than 3. My horizontal asymptote has also changed. It's no longer the x-axis, which is y equals 0. Now we're talking y equals 3. Everything moved up. So be aware, when you move the graph vertically up or down, it will affect your asymptote and your range, your output values, and also your y-intercept. Instead of being at 1, if we move up 3, now it's at 4. You can see that really nicely on your graph. All right, let's take a look at this last one for letter C. Let's see what you thought about for this one. The negative with the x. If the x changes sign, that means you are reflecting over what? If your x changes sign, you're reflecting over the y-axis. So you're reflecting over the y-axis. Please don't just ever say it was reflected. There's lots of ways you can reflect a graph, and it does matter over what. So be careful that you're saying over what, or what is it symmetric with respect to. And then what does the -3 at the end do? That's going to be a down 3. Okay, so I want you to think about what effects this is going to have on the graph. If it moves down, remember your horizontal asymptote is going to change, as will your range. So let's take a peek at that one. All right, so be careful as you type it in. Make sure you get the negatives in the right spots here. All right, so instead of being increasing, it's decreasing, because remember that would be the same as 4 to the negative first, or 1/4 power. It's 1/4 of what it was, so decreasing. My y-intercept is going to change for sure. That's going to be going down 3. So if it was at 1, now it's at -2. Kind of makes sense. And now where's your horizontal asymptote? Not at 0 anymore. It's at y equals -3. So my range values are all the numbers greater than -3. So remember, vertical shifts will affect where those asymptotes are. All right, so now I'm going to have you go the other direction. I want you to write an equation for me of 4 to the x that goes left 2. Pause the video, see what you come up with. Check your guess on your calculator and see if you are correct. All right, so we're going to make up a new function. We're going to do, m of x. And we want to go left 2. So if it's going left and right horizontal, remember that means it has to be in the exponent. And if you're going left, that means it's a x minus a -2, but most people would probably just say 4 to the x plus 2, because remember, if you said x plus 2 equal to 0 and solve how far am I from 0, you are -2 units. So just always think of it that way. Double check on your calculator, that will go left 2. Remember, that will not change. Left or right will not change your horizontal asymptote. It will change only your y-intercept. How about reflects over the x-axis? Do you remember how to do that? Pause the video. How do you make a graph reflect over the x-axis? All right, let's pick a different letter we haven't done. We'll say v of x. All right, how do we go over the x-axis? That means the output, or the y, has to change sign. That means we have opposite out front. And for that one, definitely going to affect the horizontal, or the domain of, or the, sorry, not the domain, the range of that function. Everything will be below the x-axis now instead. So being able to recognize transformations will help you so much when you think about what the behavior of these graphs are going to be. It's exactly the same as what we have for any other parent graph. All right, what else can we do with these? Well, we can solve and evaluate functions too by using a one-to-one property, or some people call it the equality property. It's a pretty straightforward thing, and I'm going to talk you through this. And here's some just basic information information again. Your bases always have to be greater than 0, can't have a negative number, and the a can't be 1 either, because 1 to any power, just 1. Here's what the 1-to-1 property says, or equality property says. If you have a to the x equals a to the y, if that's true, so we have two expressions where the bases are the same, different exponents up there, but these expressions are equal to each other. That happens if and only if, it's a very declarative sentence here, if and only if x is equal to y. The exponents would have to be equal as well. Kind of makes sense, right? If I have two expressions that are equal and the bases are equal, the exponents have to be equal too. We can use these to help us solve for different values of x. So let's see if we can do that. We're going to try one. So 8 equals 2 to the 2x minus 1. Now, I think a lot of people would start kind of guessing and checking and trying to figure out what this would have to be. And I think a lot of people sort of do that and kind of think this way anyway. So 2 to the what power gives you 8? Well, 2 to the third power, right? You can kind of work backwards and figure that out. That's thinking of the 8, though, as having the same base as what the 2 does. So rewrite 8 as 2 to the third. And then we're going to be able to solve using this what we call one-to-one property. Some people call it the equality property. If you have two expressions that are equal and their bases are the same, then gosh, their exponents better be the same as well. So we could say 3 must be equal to 2x minus 1, and I can just solve for x. So add 1. So we'll have 2x equals 4. So x would have to be 2. Okay, that doesn't mean the exponent's 2. That means the value for x that we need to substitute back in would have to be 2. And think about that. 2 times 2 minus 1. So 4 minus 1. Yep, that would make a 3. What's kind of cool is the graphing approach to this. So I want you to take a peek. We're going to type in y equals 2 to the 2x minus 1. And I want you to see how else we could solve that. So I'm typing in 2 to the 2x minus 1. Take a look at the graph. Okay, now here's the cool thing. When do you want to see what happens? You want to see when 2 to the 2x minus 1 is equal to 8. How could you do that on your graphing calculator? Well, we could trace and see when it gets close. We want y to be equal to 8. Went too far. Oh, so it looks like it's somewhere between 1.8 1.96, and then 2.1 is a little bit too big. So a guesstimate of around 2 would be a pretty good guess. Here's another way that you could do it. You could look in your table and see when your output was 8. So let's take a look. Oh yeah, 8. That was when x was 2. So you could solve it that way. Some people do this. This is super cool too. What about putting in a horizontal line at 8? And then I can see where those two graphs cross. So I could go to second, trace, intersect, and I could see when it crosses. So first curve, look at the top, is that your exponential? Yep. Second curve, is that your horizontal line? Yep. Where's my guess at where they cross? Oh, I think it's about there. Oh, 2, 8. So there's graphing approaches to this as well, but that's kind of a cool way to look at it, I think, to reinforce what we're actually saying. For what value of x, for this exponential function, do we hit that threshold of 8? Think about applications. If you're talking about exponential growth, say, of product sales, when will sales reach $8 million? You could calculate when that would happen. All right, let's take a look at the next one. This is a little trickier for people sometimes. Fractional exponents always stress people out. If you prefer whole number, remember what you can do with the 1/3. Remember, you can rewrite it as 3 to the negative first power. And I think for a lot of people, that's a good way to start because it's hard for people to think fractions to try to do that. So power to a power, we multiply. So 3 to the x equals 27. So a lot of people can just kind of guess and check here. 3 to what power gives you 27? Well, 3 to the third. But that's rewriting 27 as 3 cubed, and we're using the one-to-one property. A lot of you just sort of do this naturally, but this is what you're doing. When two expressions are equivalent and their bases are the same, then their exponents have to be equal as well. So the x must be 3. Let's go back and just plug that into the original and see if that makes sense. So I'm going to plug it into the original sentence. 1/3 to the negative third power is 27. Well, remember, negative means reciprocal, so that would be 3 to the third equals 27. Sure does. So this one-to-one property is really helpful. All right, so let's go back to our essential questions here. How can I recognize and evaluate exponential functions? Well, hopefully we know those basic features. Always increasing or decreasing. Always have a domain of all real numbers. Range is greater than 0 on that parent graph. y-intercept is always at 1. How do we graph them? Well, we can use those features, and again, we can do all the transformational shifts that we do for any other graph. So if it's up in the exponent with the x, it's going left and right. If it's outside of the exponent, like after the function, before the function, then it's a vertical shift. And the negatives, we can either reflect over the x-axis when it's out front, right, opposite, or we can reflect over the y when the negative is up with the x. So, and the very last thing, one-to-one property is a way to make the bases the same, then the exponents have to be the same as well.